Hello, this is my lab report for Lab 3, Circuits. In this lab, we will be creating and analyzing different circuits. We will compare our measured current, voltage, and resistance with our theoretical calculations. And to do this, we'll be using rules related to parallel and series resistors, the loop rule, the node rule, and rules relating to RC circuits. What we found was that our experiment's results closely followed our predicted results, and that capacitor charge will depend over time. Key principles. A big one is Ohm's law, which is V equals IR. And down below, you can see the relationship between the effective resistance and the individual resistors, depending on if the resistors are wired in series or in parallel. And then the loop rule states that if you go in a loop, the sum of all the voltage differences must equal 0. And for the current, if you have one wire branching out into two, the current of the two branches must add up to equal the original. Here you can see the exponential rate of a capacitor charging or discharging, and the amount of time it takes to fully charge or discharge will depend on the resistance and the capacitance. Reasonings and assumptions. For simplicity, we'll say that our wires are perfect conductors, and we'll also say that our multimeters are perfect and do not interfere with the circuit's natural behavior. System versus surroundings. Our system is the circuit, the surroundings are everything else, and we'll say that for most of the time, our multimeters will purely be used to collect data. Initial conditions. For the first part of this lab, our conditions will be determined by the layout of the circuit. For the second part, our initial condition will be when either the capacitor is fully charged or fully discharged. For the first part of our experiment, we'll set up the circuit as shown on screen, and we'll calculate our expected current. And that is V over R, where R is the sum of our two resistors because they are in series. And this pretty closely matched with our lab data. Next up, we switch one of our ammeters for a voltmeter. In an ideal voltmeter, the resistance is infinite, so that the current flowing throughout the circuit is 0. This theoretical result matches up with what we found in our lab. Then, we use our voltmeter to measure the potential difference across each component of our circuit. And that gives us what we'd expect if we would have just calculated it using V equals IR. Here we can see the loop rule. We start at 0, go up due to the batteries, flatline at the wires, and decrease at the resistors to end up back at 0. Another part of our experiment is connecting an ammeter in parallel. Because the resistance of the ammeter is much lower than the 100 ohm resistor, our total effective resistance of our circuit just decreased. This means that our current must increase because our voltage is constant. Finally, for our RC circuit. So we'll first attach a battery, light bulb, and capacitor all in series. On the left, you can see that while the capacitor is charging, the light bulb is on. On the right, the capacitor is done charging, and the light bulb is off. Next up, we'll detach everything from the battery, and we'll create a circuit that only has the charged capacitor and the light bulb. We timed how long it took for our light bulb to go out when we were charging and discharging the capacitor, and this lined up pretty well with what we'd expect to see. So with a 1 farad capacitor and a 10 ohm light bulb, we get tau equals 10 seconds. We're looking for how long it takes to go from 0 to practically full charge on the capacitor, or vice versa. And because of the exponential relationship between time and capacitor charge / voltage, we need about 5 tau, which is 50 seconds. Sources of error. So our stuff was not perfect. Our 3-volt battery was actually only 2.9 volts, and our 100 ohm resistor was actually 105 ohms. And additionally, there also could have been resistance in wires, and we could have done some imprecise measurement when using stopwatches and multimeters. What if we charged the capacitor with no resistor? Theoretically, it would reach full charge instantly. However, this would not happen in real life because there will always be some resistance. In conclusion, we found that the sum of potential differences over a closed loop equals 0 volts. If we attach voltmeters in series, they act like open switches. V equals IR for ohmic resistors, and capacitor charge and discharge times vary based on capacitance and resistance.